Hi, everyone. So thank you for coming, and I'm looking forward to presenting this work. It's the first work on interpreting physics in video models of its kind, although some great work has come out since then. And I'm very much looking forward to sharing what we found. So just a little brief introduction as to who I am. So I am finishing a PhD at McGill and Mila. I have a background in neuroscience and computer science, and I previously worked as a neuroscientist. And I'm currently a visiting researcher at Meta on their JEPA team, where I also lead the internal interpretability forum. I have a background in mechanistic interpretability of vision, multimodal, and video models, and I'm also the author of Prisma, an open source mech-interp toolkit for vision and video transformers. So today we're doing this new project. What inside a video world model, what is inside when it computes physics? How is it coming to these decisions that lead to the next prediction? And there are two reasons I'm super interested in this. One is for physical verification. So can we make sure we're getting these accurate and safe systems? And the second is potentially a little more scientifically risky, but in my mind, in some ways, like more deeply intellectually satisfying, where can we learn these scientific simulators in an unsupervised way? And that would be big if true, because now you have learned in an unsupervised manner a scientific simulator in which your internal latents correspond to maps in the external world. So here's why interpretability becomes so crucial for these world models, because we're not just asking, oh, can this video model like generate an accurate view of the world, or can it predict the world accurately? Like, sure, those might be useful for some downstream applications. What we're actually asking in the context of this study is, can we use the internal, almost cognitive map, as a neuroscientist might call it, the internal world model of this video transformer to act as a scientific simulator of physical processes. So let's take a step back and just look at some of the state of the art models. So here's a generation from VO, and let's just watch it very quickly. So as we can see, this is not possible. This is like a hallucination, the equivalent of a hallucination in the physical world. We just don't have physics like that, like balls don't go up. And this is the result of a model that was trained in an unsupervised way. So this is also to say that getting physical plausibility in these models is still an open question. Like, it's still not clear if scale is all you need, and if we just throw billions of videos at these models, like accurate physics will emerge, or if there's something more subtle going on. Proponents of the JEPA camp might argue that you need to predict in latent space. The model shown was in pixel space. Others might argue maybe you need certain inductive biases baked into your model, and others might argue you just need to have a really hardcore fine-tuning recipe that kind of like RLHFs the model into submission, kind of in the way that like code generation models also to some extent need to compile. And the analogy here is that the physics world needs to compile. We can't have these like impossible events happening. And in the world of coding, we can't have like dangling for loops. And coding models like work pretty well once they've been trained in the right way, and fine-tuned and post-trained and RLHF'd in the right way. So it's possible that we're facing an analogous problem. So this is all to say that these are very open questions, and this paper does not obviously like solve all of them. It attempts to take like a small bite out of this problem, and also more foundationally set the stage for this conversation for how do we do interpretability on the physical world, on video models, and what are the implications of what we're finding. So again, everything we're finding is like very new and happening in real time. So this is a very exciting area of research to work. So feel free to ask questions along the way. And if anyone also wants to collaborate or build off this work, this is like very much something that we are looking to form partnerships in. All right, now let's get into the more nitty gritty. So how does a system reason about physics? So before we enter deep learning, like cognitive science has debated this question for a long time. And you can't really answer this question from just behavior, but you have to answer on the level of the internal representation. For cognitive science, it was the mind. For neuroscientists, it was the brain. And now for us, it's like the neural net. And there is some work that proposes this idea of the intuitive physics engine, in which you kind of have these like compact, reusable states that allow you to simulate the world. So imagine like, if you close your eyes and imagine walking around your bedroom. Interestingly, some people can't imagine that if they have like visual aphantasia, but like if you can imagine that, and like the majority of people can imagine that, that's you using your mind almost as a simulator of your room, implying that you have some like internal mental cognitive map of your room that you're using to like generate this like internal simulation. And this is one kind of like hypothesis. And it's in contrast to also the idea that maybe we don't have like a physics simulator, almost like a game engine style, like well factorized mental model of the world. Maybe our brain is like a giant kludge in which we have separate networks for separate tasks, separate networks for separate data distributions, and our mind is like quite hacky. And this is very plausible because if you think about dreams, your dreams is also using your brain as like a simulator in some ways. And in dreams, you physics often breaks, like you go through walls or you fly or like various nonsense happens, which suggests that maybe our brains are actually not super great simulators. Maybe they're just like good enough simulators to do like very basic planning. So there is somewhat like tension between these two debates. Like, to be honest, this question is extremely hard to study in the context of human brains. So for anyone here who has like a more neuroscience focus, like video models are an extremely good substrate to test these like neuroscientific hypotheses, just because like measuring physics understanding in the brain is like logistically challenging. So both accounts actually are predictive, where we have these like more general like latent state models internally versus we have these highly distributed like task specific kludgy shortcuts. And cognitive scientists are kind of like, maybe this is a boring answer, but perhaps it's the most true answer, that okay, it's like a bit of both, like depending on the task. So I'm going to give one more example. So like separately from like the sort of like general latent variable generating this game engine system and this like distributed kludgy hacky thing generating the system, there's also a separate debate where even if we do have some kind of internal representation of the physical world, it might be baked in with systematic biases might be baked in. And this is more work from McCloskey on intuitive physics. And what he did is in the 1980s, he basically got a bunch of physics undergrads to perform a set of physics tasks. And this was super interesting because you'd think physics undergrads, I believe they were from Harvard, would have a decent understanding of physics, Newtonian physics, but they actually failed some of these tasks, interestingly. So here's an example. So on the task on the left, the student had to walk across the room and then drop this ball on a target as they walked. And if you really reason through the problem, as you're walking, you have forward motion. So if you're right above the target, well, I guess maybe I'll ask you guys, and like we could think about it for a second. Like, when do you drop the ball so it actually hits the target?
So the target is moving.
The target's on the floor. The target's stationary.
Oh, okay. Like I think when you are,
because the wall is moving with the person.
Mm-hmm.
Right.
Yes, sir.
Right, a little before we reach it,
Mm-hmm.
as I think Francis also said. Yeah, so you guys got the right answer, and maybe some of you reasoned through it. Maybe you guys intuitively knew it. Maybe an athlete would know it in like an embodied way, and would just drop the ball right before the target. The person and the ball are moving forward. There's forward motion, so you want to drop the ball actually like right before you reach the target, because the ball is technically going to be moving diagonally. And this is like kind of maybe counterintuitive, but most of the students got it wrong, and they would drop the ball right on top of the target, and thereby missing the target. So either maybe they're not good physics students or not good athletes, like depending on like what framing of like good physical reasoning like we want to take. Like, do we want to take this more cerebral Newtonian mechanics approach, or do we want to take this more like embodied reasoning approach? But they both like lead to the same outcome. And Separately, there's a task on the right where you have a person who has like a ball on a string and he's like swinging the ball around. And then here the students were asked like, okay, if the ball were to detach from the string, is it going to go in like a straight line or is it going to go in like a curve? And does anyone know? Or does anyone have a guess?
Straight line.
Yeah, it's a straight line because this is just like what Newtonian mechanics predicts. But a lot of the students intuitively thought it would be a curve. And Minkowski's like, what the heck, what's going on? Like there seemed to be like a systematic incorrect bias in the way humans are reasoning about the world. And this is really interesting because it also aligns with the work that came before Newton called impetus theory. And impetus theory basically made all the same incorrect predictions that the humans were making. Like impetus theory was very aligned with some like naive or intuitive understanding of physics humans might have. And if you think about it, the pattern of error is like somewhat systematic. It's always biased by your frame of reference. Like you think the object is going to do the thing that makes sense in your frame of reference. So why do I bring any of this up? Like I'm bringing this up to make an analogy in the sense where we have these video models that are now trained on a ton of ego-centric data. And it is an open question if these models are going to show these same like intuitive physics biases, where they might systematically mispredict the physical world in a way that if these video models are in some industrial pipeline or operating in a self-driving car or in a robot might lead to physical liability. We are now operating in the physical world where we cannot make mistakes. So this is just to give an example where drawing upon humans, like humans are these imperfect physical reasoners and or machines might be as well. And interpretability is just very interesting to kind of pull back, open like the hood of the car and just like see what's going on. And in the future, potentially audit these systems on a deeper level than just looking at their outputs, which is black box evals, but opening up the hood of the car and doing white box evals where we can see every step of the internal decision-making process of the network just to make sure that we're deploying like the safest systems that we can. All right. So this is a new test bed for this old question. Like I'm building off some past work by my collaborator, Quanto Garrido, that showed that JEPA is superior on these intuitive physics tasks that we'll get into in a second. Intuitive physics is just like one paradigm of measuring accurate physical reasoning. And I do want to be completely scientifically transparent here in that in a lot of these studies comparing JEPA to other models, JEPA is often trained on orders of magnitude more data than the other models. And so it's very hard to get a clean read as to what is like actually happening. And I say that just to be completely transparent. And one might push back and say, oh, okay, why don't you just train like video MAE on the same amount of data as JEPA? That's possible, but it's kind of non-trivial. It's like, oh, just like train like another like giant foundation model as your baseline. Like sure, one could, but like that's actually like quite a huge coordination of like effort and resources. So I would say it's still honestly a little bit of an open question as to like which objective functional architecture is superior here. And I'm just saying that because I know that's like a debate that's frequently had on the internet. But we don't really care as to like which one's better. We want to look at behavior and we have access to transformer internals at an unprecedented scale. So, okay. We ask 4 questions. Like we start with this question as to where does physical information emerge in the network? At the time, it was the first video physics interpretability study. So in interpretability, I'm a huge fan of just doing the most basic thing you possibly can. And asking like, okay, where is information emerging is a basic question. Like where does acceleration emerge? Is this some kind of almost like video game, or not video game necessarily, but like physics simulator, or if you think of like a physics undergrad studying Newtonian mechanics, there's like a certain hierarchical order in which you might compute physical information. You might start with computing distance and time, and then you might use that to get velocity, and then you might measure true velocities to get an acceleration. So there's like a hierarchical composition of variables in the Newtonian world. And we were wondering, maybe does the model do the same thing? Does the model measure velocity and then use that to hierarchically form acceleration? And we were approaching this like with a very open mind because we really had like no idea how the model was representing it. So we were also curious, like, how is this information organized? What does it look like? What are its shapes and structures? And again, given that this was the first study of its time, we really weren't sure what basic stuff we'd find. In language, there's a pretty strong precedent for these like low dimensional steering vectors. Like you have a refusal vector where if you steer it, you can now get all these jailbreaks. You have like a pirate vector where if you steer that, the model can talk like a pirate. We were wondering like, what are the analogs in the physical world? And are they as like low dimensional as what we might see in language? And is it highly factorized? So this is like the really nice physics engine we talked about earlier, where you can like turn dials like up and down. Or is it more distributed and heuristic and actually kind of hard to control? And is this causally controllable? Can we actually now manipulate the outcome? And also, do tasks share features? Like, is there kind of like a latent physics simulation system that is general across like various data distributions? Okay, so before we jump into some of our findings, I just want to take a pause and see if there are any like comments or questions.
Maybe one brief question regarding, I think maybe 2 slides ago. Can you comment a bit on how you actually evaluate, one forward. How do these benchmarks actually look like?
Yeah, really glad you asked. We'll get into that as we start unpacking our results as well, because we use some of these benchmarks. And these, I guess maybe just to give like a little bit of a preview, these benchmarks are based off child development literature that looks at when children hit certain developmental milestones like object permanence, spatial temporal continuity, like shape constancy, and designs a benchmark to mimic the studies that were done on these children to test their understanding of intuitive physics. So it may not be like a more conventional sort of like college grad Newtonian physics kind of understanding of physics. Like it is like a more intuitive and embodied physics. But we can discuss that in a little bit.
All right, good. Thank you.
Okay. Any more points? Okay, let's move on. So a very high level overview of our findings before we jump in. So if we have like a physics engine assumption, we might assume this like staged derivation that I'm like discussing earlier, where like acceleration is derived from velocity intermediates. And as we're really going to jump into the nitty gritty of our findings, but just to give this broad overview, we find that acceleration is decodable at the same stage as velocity without an explicit intermediate velocity state, which was interesting and also quite brain-like in the sense where the brain uses this like energy-based motion coding. So we'll get into that in a second, but it's just kind of like breaking one of our first hypotheses like very quickly. And then we also assumed like, okay, maybe there's some like Cartesian representation where you have motion encoded as like Vx, Vy, and what was like the internal coordinate system that the network was using to like store its representations? Like what was it using, like a Cartesian system? Was it using like a polar system? Was it using some alien system or some like what was it just like too incoherent? But we kind of actually find the polar factorization where the model appears to be storing variables in like a way that's separates like speed and direction. And this is also very brain-like as well. And you can decode Cartesian representations, but the polar representation seems to dominate, which is very interesting. And we also assumed, okay, if this is like a physics engine, maybe you have these like shared latent physics generating this, generating across tasks, and motion variables are reused across tasks. But we find, at least for the tasks we look at, that their subspaces are nearly orthogonal. Like they appear to be using different subspaces for very similar physical processes, which suggests a more distributed and like almost hacky approach. And further, a physics engine assumption might assume that you have these like compact state variables where motion variables like occupy like these low dimensional subspaces. But instead, actually, unlike language, we find that direction spans tens of orthogonal components. So when you steer, you're not just steering like a single feature direction, you have to steer this like large, like bulky object that is like 60 dimensions. And it leaves this like interesting open question where obscuring in the physical world, not just the physical world, but like the video world, is a pretty different data distribution than language. So a lot of like the mech interp like language assumptions that people are making like break pretty quickly. So this was like quite cool. And further, a physics engine assumption might assume these like object-centric state slots, like maybe like motion is decodable from like specific like spatial or temporal patches. And at least in the unsupervised video encoders that we found that don't really have inductive biases enforcing this information, we find that direction sort of like diffuses across all the patches in a way that is not really spatiotemporally factored. And so we're going to go into the nitty-gritty of our findings. One thing I just want to say straight up is when this paper was going through reviews for ICML and it was ultimately accepted, but like one of the major critiques is that we don't use that many tasks. And I think in some ways this is a very fair critique, but in other ways, task design for the physical world is like quite challenging and quite tricky. And there is, I guess, like decades of cognitive science research that have been crystallized in some of the intuitive physics tasks that we're about to get into, and like research teams like built around making the data sets themselves. So that's all to say like data sets, benchmarks, and really thinking through how to set up these problems are part of the research and super important and like super worth working on as well. Because for us, it actually wasn't really obvious. And even in the case of this, like in a lot of our findings where direction and intuitive physics are like in these written to like different subspaces, one could argue that, yeah, these tasks are both synthetic data, but they weren't generated by the same engine. So maybe there's some like really subtle like distributional difference here. Okay.
I guess one question I have here is in terms of task design, like, I mean, I feel like task design is it's a moving target. So, and like, depending on who you ask, like it can be application specific also, like somebody working on autonomous vehicle, they have like a different set of tasks than like someone working on, let's say, in a drone, right? Or YouTube videos, like different kind of tasks. So, and even within one segment, let's say autonomous vehicle, there if you want to tackle like edge case, the tasks are different than regular case, right? So how do you sort of like go about it in an academic setting that you can claim that the solution you have is general enough? Like, I think that's a challenge. So I'm curious to hear your thought.
Yeah, I think that's a super good point. In the sense, yeah, self-driving car data, like drone data, whatever, are all going to be quite different. Like I would say this paper is so early and almost pre-paradigmatic that using these very academic synthetic data sets is a good start just to develop intuitions. But as this field of video interpretability, which is so nascent, matures, like I would love to see someone run this cross-embodiment study. Like, is it the same circuitry that is activated for your humanoid, for your drone, for your whatever model that you are maybe like fine-tuning or adapting, and do similar mechanisms like seen across like very different models trained on very different data distributions. And there is like a lot of discussion about cross-embodiment, like how easy is it to how general are foundation models in robotics, right? Like, can you very easily like fine tune different foundation models for like various tasks? And the interpretability perspective on that will also reveal a lot about physical reasoning of the cognitive sciences, but that work just like, it's just like too early for that work to exist. Okay, so let's now, we're almost done with context. Let's now get into what we are actually studying. So most of our analyses are on this JEPA video encoder. And we also look at video MAE, but JEPA is mainly our object of focus. And this is also because JEPA is one of the best open source models out there that's easy to do research on. And JEPA 2.1 was trained on 1 billion videos, I believe. So it's going to give the highest performance. And JEPA basically has these like three transformers. You have a context encoder and a target encoder, and you feed the same video clip into both the context and target encoder. You project them into like this latent space, and then you have a predictor that's predicting these masked spatial temporal blocks and comparing them to what was encoded by the target encoder. And this gives like a form of labels. And all of this is like done in latent space. And you have like this exponentially moving average of between like the context encoder and the target encoder. So for those of you who are familiar with dyno optimization, this is not quite how dyno is optimized, but there is some like similarity in that you have these like this like teacher-student setup. And this is a way to learn robust representations without any labels, and in this case, without optimizing for pixel reconstruction, which is JEPA's claim that reconstructing pixels is quite noisy. So by focusing on latent space, you're able to like isolate dynamics and not worry about like reconstructing pixels. And one example I give to make this intuitive is if I tell you there is a balloon behind you, it really doesn't matter what color the balloon is. The balloon could be like red or blue or green. Maybe when I say that, some of you imagine that there's a very specific balloon behind you. Maybe some of you manage a red balloon, but the point is that it doesn't matter because balloon is at the right level of abstraction. And in the same way, JEPA is attempting to like learn representations of our physical world that are at the right level of abstraction. Okay. So now let's get into the earlier question that was asked by Francis, if what benchmarks we're actually looking at. So this is called the intuitive physics data set. And I would also recommend looking it up. I don't think I could have embedded a GIF in this PowerPoint, but like basically, if you look at this like top row right here, you have a scene in which there's nothing in it. And then you have this break frame where a cube will suddenly appear. And this is supposed to violate the fact that like objects like don't appear and disappear in our reality. And that's something we have learned. And so this is one example of like object permanence kind of breaking. And every example is matched with a pair example in which the symmetry is preserved. So for the top row where a cube suddenly appears in the breakpoint, you have a matched point where the basically like the cube is always there or the cube is never there. And the reason that you have these matched pairs is to get rid of like pixel level and texture level confounds, which for a lot of physics data sets are a huge problem, that you're not actually measuring dynamics, you're somehow measuring some like some pixel level or texture level detail. So really refining the data sets has been a work in a subfield in academia. And the middle row here, you have this like red cube that goes like behind this wall, and then it just like transforms into like a red cone. So you have this idea that like shape constancy is violated. And these terms come from like developmental psychologists who have been like looking at when babies reach certain milestones in their understanding. And on the bottom row here, you have this ball that's going across the screen, and then it like abruptly reverses trajectory and like goes the other way, some kind of inconsistency. And what previous work has done on the right, so this is by my collaborator, Quentin Garrido, is they used like a violation of expectation framework. And this is also based off studying the surprise reactions of babies. When, in order to know if a baby has learned a certain concept of the physical world, you have to measure its surprise, where the more surprised the baby is, like if an object like disappears or something, the more it implies that it had some kind of preconception or some kind of internal world model of how it expected the world to work. So this is the framework where you can look at a model's internal world model by measuring how surprised it is about certain things. And its surprise suggests that that's not really what was predicted. And your surprise is just like the loss. So if you look at the loss and if your loss changes, and your loss goes up, this implies that you mispredicted this incorrect situation. And that's actually what you want if you have like an accurate view of the world. So if you have an accurate view in the world, like the loss should spike when, triangles like transform into cubes. And this is not necessarily the only way of going about things or the perfect framework, but it is one set up to measure this like intuitive understanding of how these video systems might be encoding things. Okay, so basically we do the simplest possible thing where we train like a binary probe to classify possible or impossible events. And for those of you who are curious, I really recommend checking out Intuitive Physics 1. We tried this on Intuitive Physics 2, but unfortunately, Intuitive Physics 2 is just too hard as of now. And that's something that future video models will have to see if they can solve. And we tried this across like various JEPA sizes. So everything from like JEPA large to JEPA giant. We also tried it on video MAE. And basically what we find is that across model sizes, there is a predictable zone of layers where physical reasoning, as defined by this impossible task, like appears to arise in a consistent place. And this is 1/3 through the model, and we call this the Physics Emergence Zone. And in the Physics Emergence Zone, it appears that like physical understanding like gets constructed. And on the bottom on the x-axis here, we have layer fraction. So how deep in the model we are, and this is like normalized against like the final layers. And on the y-axis here, we have like accuracy. So this was kind of interesting because it was like a pretty consistent result. And this is somewhat of like a basic test, but we need to run basic tests because we don't really know anything yet, and we need to get proxies. So we then ran like a bunch of other tasks. Like we ran shuffled videos, we ran intuitive physics, we ran something V2, which is like a hybrid sort of data set. And then we ran these like semantic tasks like ImageNet, and also semantic video tasks, like counting the number of objects in a frame. And what we find is direction emerges. The Physics Emergence Zone appears to be tied to direction in the sense where tasks that heavily involve direction, like shuffled video, appear to show similar signatures in this, while tasks that don't really require the use of direction appear to be way more gradual and like way more sloping. And this was super interesting. So now we're hypothesizing in a somewhat correlational way that the Physics Emergence Zone is bound to some kind of like spatial temporal coherence and some kind of direction prediction. All right. So we also find that, just to quickly go back here, that like our representations are degrading. And this suggests that the best physics representations are in the center of the network and not actually at the end. And this is practically useful if you're using these representations downstream. The kind of naive thing to do is just like use like the final representations, but the more I'd say like sophisticated thing to do is to find the layer at which your representation is most faithful. And this is very similar to past work on Clip and Dino, showing that in Clip and Dino as well, the middle layers have like the most like spatial temporally rich information. And this is super interesting. There are a lot of like cognitive science reasons that this could happen. It could be that the output is like too selectively optimized for like a given task, while the middle layers are like actually the most rich. Okay, so we test this hypothesis on the violation of expectation task, where we feed in representations from the middle layers and the later layers, and we find that the middle layers really have like the best performance on the task. And this might apply to more practical like downstream robotics tasks, but that also remains to be tested. Okay, so intuitive physics is still quite vague. And was the surprise metric similar to surprisal? Yes, I believe this is surprisal, although I'm not sure which definition of surprisal you're referring to. Okay, so the intuitive physics task is still kind of like a vague concept. So what if we debundle intuitive physics into more precise physical variables? And now we have a new data set of a ball rolling in controlled angles and directions generated with a physics engine kubrick, which is really easy to use, by the way. It's really useful for generating data. And so we measure Cartesian coordinates, velocity and acceleration. We measure polar coordinates, speed and direction. And we find that speed and direction emerge at different depths. We find that speed is decodable from layer 1, while direction only emerges into the Physics Emergence Zone. So what are we looking at here? On the left, we do this Cartesian decoding where we look at Vx, Vy, Ax, Ay, and we find that they emerge together at the physics emergence zone. So they're following this like similar pattern, but they entangle magnitude and angle. And when we look at these polar results, we find that scalar speed and acceleration magnitude are decodable from the earliest layers. And you have this dissociation where direction is now emerging in the physics emergence zone, while speed and acceleration, here acceleration defined as acceleration magnitude, are decodable almost immediately. And direction is the variable whose accessibility defines the physics emergence zone. Acceleration does not require an explicit velocity intermediate. That's interesting. You can compute it very quickly. And also this looks very similar to energy-based motion coding in the brain, where you have specialized neurons that can get at scalar speed and scalar acceleration very quickly. And then ultimately your brain has to like integrate across neurons to get direction. Okay, so this result is extended to multi-object findings as well. Here are various curves for predicting just various, the directional velocity of these various moving objects in the Clever data set. So we're just showing that this generalizes to data sets in which you have like multiple objects in the frame. Okay, so this is again very similar to the cortical motion hierarchy, in which motion, energy, and speed sensitivity are read out early in V1, and position invariant direction selectivity arises later through pooling in the MT, and JEPA produces this hierarchy without being trained for it. So in some ways, maybe this result is obvious, but to me, I wasn't expecting to find it. So to see these neuroscience results emerge naturally has been like pretty cool. Okay, so we find in the physics emergence zone that direction goes from retinotopic to position invariant. So in the earlier layers, direction info is retinotopically fragmented, the per patch probes fail, and at the physics emergence zone, we have this finding that probes trained on one half of the frame transfer to the other half. So what does this mean? We see on the left here, the shaded lavender region being the physics emergence zone, and the blue violin plots here are doing per patch probes, like where to train a probe like on any given patch. And we find, interestingly, that the per patch probes are pretty bad, and you need to kind of like linearly sum or do pooling across all of the patches. In video models, they're called tubelets, across all of the tubelets in order to get a good decoding accuracy. But at the physics emergence zone, that appears to change, and you can suddenly do per patch decoding. And if we were to like look at a heat map, we see this transition zone between, in this case, layer 7 and 8. So this is right in the center of like the physics emergence zone in the lavender region, where these per patch probes are all not really decodable. You can't really decode direction information, but at layer 8, you can suddenly decode direction information from any given patch, and it's like evenly like diffuse across the whole frame. So this was like very interesting and a little surprising, but I thought it was very cool that we could go down to this level of like mechanistic specificity. And further, we find that the geometry at the physics emergence zone was really, really clean, where we trained these generalized linear models, which come straight from classical neuroscience when doing like per neuron prediction. And we find that if you look at the MLP layer of layer 8, you see this perfect direction tuning. So every neuron specializes in like a preferred direction that almost perfectly tiles like a unit circle. And here's like a raster plot, like neurons are sorted by their preferred direction. And this result is like kind of what neuroscientists would like hoped to have found if they had the ability to cleanly measure direction neurons in wet brains, but that's like quite hard to measure too. So to so easily after maybe a couple months poking around, like find this neuroscience result in a video encoder was like very it was very promising sign, promising for neuroscience at least. So if there are any neuroscientists here, like please research these models more. And again, we find these like almost perfect GLM style like curves that predict direction like very accurately, like with a high R squared. So to have this like beautiful like circle of like specialized direction cells in the physics emergence zone was like, wow. And here's like another representation where in layer 0, you might have the direction tuning vectors like oriented in a sporadic way. But now in layer 8, you have this like organized direction tuning that perfectly tiles the space. Okay, so we saw a textbook style MT, a textbook MT style population code, and it was cool that we could recover the geometry. It's the same population structure as direction selectivity from like the 1980s neuroscience literature, which I recommend checking out. It's like quite fascinating. And same as optimal probabilistic readout from like neuropopulations. And again, like more work on population vectors in the motion cortex that are good, like neural inspiration. Okay, just as a control, we ran a similar test on speed to see if neurons were sorted by preferred speed. And there is some speed preference, but it's like very bucketed in this and not really evenly tiled in the sense where like these like higher speeds appear to be a bit more evenly tiled, while like the lower speeds are like not necessarily the case. And this could be an artifact of how we constructed our data. And there does need to be more research in this vein, but it is giving some sense of like to what extent are different neurons like specialized for different speeds. Okay, so how does steering work? Steering has become super important in language, and it's often conceived of, okay, like we have like a few feature vectors, like one feature vector, a refusal direction, or etc. And it's a gold standard for causal control because it means like your feature actually systematically impacts your output. And what is a feature? That's its own question, but oftentimes it's like a direction or like set of directions in latent space where if you steer those directions or like causally up them or down them, they impact your generation in like a systematic way, and in a way that's invariant, in the sense where if you steer a pirate feature, the model will like in most circumstances, if not all circumstances, talk like a pirate. So yeah, language, one-dimensional feature. LLM's refusal direction has like some like great past work on that as well. We find that in video encoders, though, that physics-related variables are dozens of dimensions. So if you look at this graph here, on the bottom, again, you have layer fraction, and on the y-axis, you have like number of orthogonal probes. So we measure the feature size by the number of orthogonal probes it like we need to delete that information from the network. And it's a simple method, but we describe it more in our appendix. I'll keep it short just for the sake of time. But we find that direction basically is 40 dimensions in JEPA large, and like speed is like 20 dimensions, and like the intuitive physics task itself is like 18 dimensions. So measuring like the sizes of various physical objects, I think, is also an open area of study that I would like love to see more work on, where why is direction like so large, and like why is speed like smaller, and this is generalized across like more diverse data sets. And the point Nahid was making earlier about drones and self-driving cars and etc., like what are the sizes of like various physical variables and like these various situations. So would absolutely love to see more papers on that. If anyone here works on this, like please reach out to me. And we also then steer with 20 coordinated probes. Like if we steer with like a single probe, like we're unable to actually change direction. But if we steer with 20 coordinated probes, we can now actually change like the direction of the ball as measured by like a downstream probe. So we have these like population level interventions, and there is an open question for neuroscientists or cognitive scientists where it's like, what are the implications for the brain? Like if we think of our brains, like what is the dimensionality of various like internal representations is like a very exciting question that is very hard to answer in biological neuroscience. Okay, so we have these like parallels to neuroscience. We have speed early, direction late. We have these circular population codes. We have local to global pooling. That's like retinotopic to position invariant. And this is like very similar to the world dynamics, like objective, like brain-like processing, like falls out of that. Okay, so we are giving these two tasks, and now like what is the connection between the two? And again, the style of this paper is kind of following this like almost 1980s cog-sci style, where instead of machine learning's current paradigm of just like looking at as much data as possible, we are instead looking at very carefully designed tasks, with the reason that most of the physics data sets out there are baked with like visual confounds where you're not actually measuring the thing you think you are measuring. I can say more about that later. But like, we just wanted to know the relationship between these two tasks in terms of internal representations. So do they share any internal shared representational space? For example, like, is this is the synthetic ball on the right, is its speed and direction, or the internal variables encoding for that like reused? Is that the same latent space as the is that the same subspace and latent space as the intuitive physics task on the right? There are possibilities here, right? Like the two tasks may reflect some like generic depth dependent effect, or some like generic like latent variable that's even more downstream. It could be compositional reuse, which is like this video game style, physics engine style, shared latent space that's like general across all tasks. We could also have circuit reuse, which is different from subspace reuse, in that the tasks could rely on shared circuit level computation without sharing latent representations. So they might share the same attention heads, for example, but the attention heads might be writing into like different subspaces. Okay, so we already rolled out the generic effect across all tasks because we saw highly semantic tasks did not solve the problem. Now compositional reuse in latent space, we take the principal angle between the direction subspace and the intuitive physics subspace, and we find that these subspaces are nearly orthogonal, meaning that they don't overlap. These are like different subspaces. And in some ways, this result was like kind of frustrating. I'm like, oh, okay, are we just like writing to like these task-specific points in latent space? Like, we only look at two tasks. We need to look at more tasks. So again, this is a call for open research. Like, we need to be looking at way more things. But it is a little frustrating. It's like, okay, maybe this thing is actually kind of kludgy. And then though, we discovered that these two tasks do share circuit level machinery. So they both use, so to be clear, the word circuit is a little bit of a misnomer here. We don't mean like the fully connected graph. We actually mean like the weights of the neural net itself. So maybe like a weight-based or like network-based substrate might be a better way to frame this. But terminology is also, we're trying to also like not be confusing. So we look at the attention heads, and basically on the right here, we are measuring attention heads by average distance at what they attend to. And this is just like feeding in several video data sets and just measuring like average distance. And we find that in the physics emergence zone, with these dark blue heads, there's a blooming of highly local attention heads, like highly local in both space and time, that like emerges as like this crop of highly local heads, like processing probably all this like local spatial temporal information, and then they kind of disappear and the heads become quite global. And this result is like quite cool and like quite striking. So then we're just like, oh, okay, like a subset of attention heads becomes spatial temporally local. We ablate these heads and we're able to basically destroy performance for both the direction and intuitive physics tasks, while ImageNet remains the same. So now we have like a causal ablation where we causally erode performance in our direction related tasks while preserving performance in our static tasks like ImageNet or that don't require direction. And this is the strongest evidence against the engine style optimization with compact reusable latents, and this instead suggesting that maybe everything is written to like quite a different subspace, but it's the similar circuit-based, circuit level, or like substrate level, network level, weight-based level, attention head level, maybe MLP level mechanisms that are responsible for similar computation. Okay, so yeah, here's our ablation, like direction we're able to reduce performance, while for intuitive physics, we are also able to reduce performance while ImageNet remains static. ImageNet's only at 33% because we're using linear probes. But these results also hold for more sophisticated nonlinear probes as well. Okay, so this does not seem to be a physics engine. It appears to be a distributed task-specific code where strong physics behavior coexists with no shared low-D state. Direction is high-dimensional, distributed, ring-shaped, occupies an orthogonal subspace from the impossible task. These findings are difficult to reconcile with some of the intuitive physics as like this beautiful engine accounts. And I just want to say that this was super interesting to run. A lot of the difficulty on our end was how do we even measure physics? What data sets do we use? Like, this field is extremely young. So the more people who work on this, the better in my mind. And again, like, please feel free to like reach out if you're interested in working on these problems or collaborating, because like I just think this research is so important. And I also want to say that these results that we find here somewhat contradict other results the community has found, not in video, but in climate, where climate models, there's some work both by Theo Macmillan at Stanford and Rio Fear at Polymatic, and I think there's some research at DeepMind now as well, that basically like asks, can you train a climate model on climate data, and then can you have like these internal representations that map to, in their case, like typhoons or various like weather primitives that emerge. And they appear to find examples of successful, I don't want to like, I don't want to overclaim their results, but it's, what I'm trying to say is that it's possible that in climate, or like systems trained on like different types of data that are less messy than video, which is basically like the entirety of like YouTube-esque data, like a system that's trained on very careful climate data, all from the same distribution, if it's on walrus or something, might have cleaner latents. So I don't want this paper to be interpreted as, oh, we completely ruled out like the shared latent space hypothesis. We can't claim that. We haven't looked at enough things. This is why like more research in this space is so important. What we can say is that we see some evidence based off these tasks in this context that that's not true, which I find a little sad, actually. I wish it were true. It would be a very elegant way for a system to operate. But let's talk now about the implications for steering, safety, and embodied AI. So basically like the LLM style single direction activation edits don't work for video. So we need like population level steering tools. Video and sensor data is just much more high dimensional than language. So a lot of people used to think, maybe still think, that like you just extend the methods of language, but I would argue that this is like a fundamentally different domain with a fundamentally different data distribution. The Physics Emergence Zone, not output features, is where physics information develops and then right after concentrates most strongly. So if you're using JEPA latents to do reward shaping, or if you're using, just saying bye to someone in the chat, if you're using JEPA latents to do reward shaping, or there was another paper that was using JEPA latents to improve physical plausibility in image generation and video generation. Potentially you want to take like features from the center and not features from the end. And the bridge to embodied AI alignment is biological brain interpretability methods. And what we did and didn't test. So again, just clarifying our limitations, we tested encoder only masked objectives. Autoregressive and diffusion models are in our follow-up, have some interesting results there as well. We tested a single ball data set for fine-grained analysis. Clever replicates direction emergence multi-object. We did not test these more sophisticated physics dynamics like contact dynamics, force entrance, and long horizon causal reasoning. We would very much love to test that. So if anyone, again, is working on this, would love to collaborate. And what is next? So we want to apply this framework to autoregressive and diffusion models in more depth. We want to push for richer physics. We want to train, this one's like a little bit more neuroscience-y, but we're just wondering if the circular population code we found, if we can induce that to be spatially organized based off some work that came out of the Yemen's lab at Stanford. And then we want to use the steering subspace as behavioral control for downstream embodied applications. Namely, can we now like steer robotic arms and etc. So thank you everyone for listening, and thank you to my co-authors, my advisors, and the JEPA team that used to be at MetaFair. And thank you everyone here for listening. We have a long-term agenda for neural-inspired robotic alignment. That's a collaboration between the robotics, neuroscience, and like mech interpret safety communities. So it's like a very fun mix. And we are expanding physics to include contact dynamics, force friction. So expanding sparse coding. We did not bring in any sparse coders or diffusion decoders to interpret immediate latents, and also embodied control, or turn that high dimensional direction subspace into a steering tool for downstream embodied agents. So feel free to reach out, and thank you for listening. If there are any questions, I'm happy to hear. Yes, Antonius.
Yeah, thank you. I had one question regarding the way I understood this pairwise accuracy was reported in Intuitive's physics dataset, which was I was working also to repeat use. Was taking as an output the features at the end compared to your comparisons with a physical emergence zone. And the task was a bit more easier because you had these pairwise surprises of your possible and impossible models to compare. So what I didn't understand specifically, maybe I have to look into the paper, was how exactly we get into these intermediate physical emergence zones, and if we need to train probes with some type of supervision, basically, from the labels of videos, of possible or impossible videos.
Yeah, I can go into a little bit more detail, and also just make sure I understood your question correctly. So the data set we used was IntPhys1, and there are various sections of that data set, one of which is unlabeled. We didn't look at the unlabeled one. Like we were using labels for possible, impossible. Like we split up the labeled section into our like training and into our test.
Exactly. So this is what I was mentioning, that there is this 01 or 2 or 3 splits depending on the implausibility induced. And just a small comment that I had to make was like, I tried getting the same results with the JEPA 2 largest model on this simple intuitive physics pairwise evaluation, and it wasn't always possible, as to say so. And also in the original papers, the release point online for VJEPA uses sign and consigned embeddings, where the results are reported with rope and different activation functions. So I think this may matches a bit your intuition on how you train these models and the amount of the data. And I think there was also an ablation on what type of data you have to look. And also I was looking at some Twitter threads about the invisible hand of physics paper. And yeah, if you want to share maybe your intuition there about where someone discovered a method to probe similarly intermediate layers of generative models to discriminate in this same fashion on intuitive physics videos, whether they were possible or not.
Yeah, I'm sorry. These are all like great. This is all like great context, just like what is happening with the invisible hand of physics results. Like, do you have like a specific question, or is this more like general commentary on these things?
Well, one thing that I couldn't think of is like, how would you use the same process on any type of generated video to find violations? In my understanding, this is a much more difficult task. So yeah, I don't know how one should go about it. Imagine if you just have some generated videos from video diffusion models. I don't know how one can use the intermediate representations or to detect physics plausibilities.
Oh, are you saying that if it's a diffusion model, because you're doing like step-by-step like denoising, it's like hard to get like latents in the same way, because you're doing like weight resharing, basically?
Yes.
Yeah.
And I was referring back on the inverse sampling on the invisible hand of physics paper, which I've seen you were debating on one of Twitter threads, where basically they try to reverse this process, but feeding the intuitive physics videos. And there, similarly, you have to train probes to classify possible versus impossible physics. And in some settings, they might beat JEPA 2, but it depends all again on the data it was trained on the number of parameters these models have.
Yeah. So I think there were like two separate points. Like one was, or I guess like in that thread, there were kind of like 3 points made. The first point being like, how do you probe diffusion models? That's something we're releasing a follow-up to this, and that's something we discussed. And also the invisible hand of physics that proposes their own method. The second thing was a more broad point. It wasn't even about probing these models. It was just about the fact that there's currently no good ablation that systematically varies data set model model size and the compute it was trained on. So getting like a systematic scaling law for physical plausibility just doesn't exist. And in some ways this is understandable because this is like a lot of compute, and training these models is quite difficult. So to get like a dedicated team to like train all these models to get a clean scaling law would require quite a bit of like financial capital and also maybe political capital to just like make the study happen. But the reason this is important is because there are all these like claims out there that like JEPA is superior. And I mean, I'm on the JEPA team, so it's like I'm just trying to be as like scientifically rigorous as I can. And like some people on the team might disagree with me. I don't know, but just trying to be as like scientifically rigorous as I can. The claim that like JEPA is superior is often attributed to this optimization in latent space, or it's like joint embedding predictive architecture. But JEPA is also trained on 1 billion videos in a way where its comparisons are not. And in the Invisible Hand of Physics paper you mentioned, they were showing you can decode possible versus impossible physics from diffusion models. And some of the commentary, some of the pushback from one of my co-authors, Artem, and myself as well, is the diffusion models they were testing on were like 1 billion, 3 billion, while the models here are like 300 million. It's like an order of magnitude bigger as well. So our question, at least in my mind, was never like, oh, diffusion models like can't do realistic physics. They can to some extent. The question was always about like efficiency. Like if you can get similar results with JEPA on like a much smaller model because latent space optimization is more efficient, then that's a boon. But right now, all of this is speculation because the systematic scaling laws study for physical plausibility just has not been run. So if anyone here is like listening to this and wants to run that study or collaborate, like please also like message me if you're interested. I'm not sure if that was clear or more confusing.
Yeah, no, thanks. It was a pretty informative answer. I mean, because it doesn't have a clear question, I get it. It's difficult.
Yeah, the third point of that thread, that was a really fun thread, very information dense thread. But the third point of that thread that someone else made is that a linear probe is pretty insufficient to measure these physical variables. And I think in some ways they're right, but also linear probes are really simple. And sometimes doing like the simplest thing just to like localize information is effective. So not claiming here or not trying to imply that like linear probes are like the be-all, like end-all method. I think this is like literally just the beginning, and future work will either like corroborate or add nuance and to these results. Okay, are there any more questions? Otherwise, maybe we can wrap up.
Yeah, I guess like since we are over like 6 minutes, we can wrap up. And I think we all have Sonia's email in the slide. So yeah, feel free to reach out for collaboration or yeah.
Yeah, absolutely. This is a really hot area of research. So anyone wants to collaborate or be advised or co-advised, then happy to chat. And thank you everyone for listening. And it was lovely to meet everyone. Thank you so much for hosting me. And I hope everybody has a wonderful day.
Thanks.